Hello everybody. Today we are excited to present you our project, XBOT, a spatially aware, voice-controlled, 5-axis robotic arm powered by X-Core AI. Now, I would like to introduce our technical director, Andrew Kavanaugh, a principal field applications engineer at XMOS, and a URI graduate in 2008, which was followed by his graduation from WPI in 2013. Andrew is pictured on the left. Pictured on the right is our consulting technical director, Chris Rothwell. Chris is a former director of advanced technologies and a URI graduate in 1981. Now I would like to introduce our team. Our team is comprised of 3 ELECOMP designers. First, we have David Quevedo, a computer engineering student, myself, Ian Newman, an electrical engineering student, and Noah Hawkins, another electrical engineering student. And now for a company overview. Our project sponsor, XMOS, is headquartered in Bristol, UK. They are a fabless semiconductor company, and their mission is to change the way systems are deployed on silicon. They do this through their advanced microprocessors, such as the X-Core AI. XMOS is employed in many fields. As a deep tech company at the leading edge of IoT, Internet of Things, they strive to provide embedded computers for any application. Now to our project motivation. Our project motivation stems from the 3rd generation of X-Core AI. This generation has DSP, digital signal processing, plus AI and I/O processing. These features boost and give an edge over its competitors. It also features nanosecond timing accuracy, full-fledged SDKs, and a software framework that helps to minimize power consumption to under 55 milliwatts. These optimizations and streamlined pipeline allow the X-Core AI to reach 1,600 megafloating points operations at a rapid 800 MHz clock frequency. Additionally, the processor's software-defined flexibility enables it to be applied in numerous ways, as shown on the figure pictured left. The X-Core AI can be used as an advanced microcontroller, the brains for an AI-enabled device, a versatile FPGA, and a real-time processor to analyze and provide meaningful data, such as intrusion detection in real time. XMOS strives to back these claims and support marketability of their chip through our project.
Our project's anticipated best outcome is to refine a robotic arm to showcase XMOS's X-Core.ai chip capabilities. This includes replicating last year's successful demo, creating an error-free PCB for better hardware reliability, and implementing precise control for at least one axis using low-level algorithms. This will be demonstrated using a new demo featuring object manipulation between 2 locations. Additionally, we would like to integrate machine learning for predictive maintenance. Achieving this ABO will provide XMOS with a robust demonstration of their technology for marketing and customer engagement.
Our team was able to accomplish our anticipated best outcome, which included reproducing the previous team's demonstration, which was able to be done earlier in the year, as well as producing an updated PCB featuring a second QSPI flash, rerouted microphones, and additional test points. This was also able to be accomplished earlier in the year. Lastly, we were able to successfully generate an AI model for object detection. This was something created in the latter half of the year to successfully perform our final demonstration. I wanted to highlight some of the key technical accomplishments achieved by our team this year. Beginning with the hardware side, we were able to successfully reroute the microphones to tile 1 on the PCB. We were able to add a second QSPI flash to the board to flash the second X-Core.ai individually. We were also able to add more test points to streamline debugging and perform various tests once the board was fully assembled to ensure that it was working as intended. This included continuity tests and checking test point voltages. On the software side of things, we were able to successfully recreate last year's demonstration. We were also able to perform motor inspections. We also ran GTK wave simulations, which helped simulate the PWM signal that we would be sending to the motors. We also were able to tune some of the parameters to get more control, as well as generating an AI model for object detection, and we finally made a successful final demonstration.
Our XBOT project will result in a competitive advantage for XMOS, which includes, but is not limited to, market diversification, cost efficiency for customers, customer engagement, and will provide scalable solutions. This slide shows the high-level system architecture of the XBOT project, outlining how all the components work together. At the core of the system are two XCore.ai processors. One handles motor control, powering the arm's movements, while the second processes voice commands, allowing the arm to respond to user instructions. The robotic arm itself features 5 axes of movements, which are all controlled by stepper motors. Each motor is linked to the motor driver modules, which are integrated with the XCore.ai for precise control. For sensory input, microphones are connected to tile 1 of the PCB, enabling the voice command functionality. A planned addition is the integration of a camera for object detection, which will enhance the arm's ability to identify and manipulate objects. Power is distributed through switching regulators to ensure stable voltage levels for the motors and electronics. Test points have been added to key locations to simplify debugging. The block diagram encapsulates the system's complexities while highlighting its modularity. By refining the setup, we aim to achieve precise motion control, seamless voice command integration, and potential AI-driven object detection.
My technical accomplishments mainly contributed towards the inverse kinematics and the machine learning model used on the project. In regards to the inverse kinematics, I primarily focused on getting the robot's end effector to reach a desired location, pick up an object that we 3D printed, and then move it to a different desired location. This first required full control over the servo motor. The servo is the motor that controls the robot's hand, and the hand is controlled through PWM signals, where the different widths correspond to how far the hand opens and closes. From there, I was able to work through the legacy code that was written from last year's team to work on the inverse kinematics. I first started off by understanding where the 0 point of the robot is, and then understood what the limits are so that the robot can move to a desired location in a safe manner. Once that was fully figured out, I then shifted my attention to the machine learning model aspect of the project. I used the You Only Look Once, or YOLO model. The benefit of using YOLO is that it not only determines what an object is, but it also determines where it is through bounded boxes. This is very important as we used an ArduCam and placed it at a known location away from the robot. We used the model to then recognize which of the 4 3D printed objects we placed out are. So that way, once it recognized where the image is, it transferred its location into the code for the robot to then pick up and move it to its base position.
Hello, this is Ian Newman. I am one of the designers for the XMOS XBOT Capstone team. I am one of the electrical engineers who helped design the PCB, and for my individual technical accomplishments, I was able to add a QSPI flash onto the existing layout, as well as routing the JTAG, Xcores, and QSPI flash together in a daisy chain configuration, allowing us to send the data through each of the systems simultaneously, and this will also allow us to use the extra processing power to add things like the object detection using an ArduCam and the voice activation that we had already had access to using the microphones, and other complicated inverse kinematic operations and other things that we could expand upon by having other I/O pins to add on to. The other things I did was allow for continuity checks and short checks via a voltmeter using test points for 24 volts and 5 volts, as well as a ground through-hole test point, allowing us to easily hook that on to an oscilloscope or whatever else would be necessary in the future. Thank you.
These are my technical accomplishments. To begin, I ran the previous team's final demonstration on the current version of the XBOT. This gave me a good idea of how the arm moved and some of the constraints associated with the arm. Another key technical accomplishment that I wanted to highlight was the work I did on the PCB. When we began working on the PCB, we were given a wish list of ideas that the previous year's team wanted done on the PCB. This ranged from including a second QSpice flash to rerouting the microphones from Tile 3 to Tile 1 on the XCore.ai. That task was similar to the other tasks associated with the PCB, where it required looking into data sheets and port maps to make sure you're sending the correct signal to the correct port. Lastly, I wanted to highlight some of the tasks I performed when the PCB finally arrived. When the PCB arrived, there were some components which still needed to be added to the board. This included some of the through-hole components, like the headers, or like the power connectors, as well as some larger surface mount components, like the crystal oscillator. Once the PCB was fully assembled, we were able to perform some tests to ensure that the PCB would work as intended. This included a continuity test, which made sure that there were no shorts on our board. We also powered the board using a voltage supply to ensure that the test points would read as intended. Before concluding, I would like to acknowledge the people who made our team successful this semester. I would first like to thank our technical director, Andrew Kavanaugh, for lending his knowledge to the team, providing valuable support with our project on both the software and hardware side, even outside of the traditional working hours. I would also like to thank our consulting technical director, Chris Rothwell, for the support he provides as well, ensuring that our team is making good progress and providing his knowledge based on his experience with PCBs and motors. We also appreciate the care he has for the team, despite being a consulting technical director for many different projects. I also would like to take this time to thank Dr. Sunak, the ELECOMP Capstone Program Director, for gathering all the sponsors that made Capstone possible. I would also like to thank him for the care he takes in assigning each designer to each project. The XBOT project was our team's top choice, and we appreciate him placing us on this project. Lastly, I would also like to thank you for watching our video and learning about the XBOT project.